Now, in order to contract, it all begins with stimulation by an axon terminal. That's how we started the class. We said, okay, nerves carry axons which then branch, and axon terminals then form neuromuscular junctions. Okay. So, what's going to happen if this is the axon terminal? It's going to form a neuromuscular junction with a muscle fiber, a muscle cell. At the site of the neuromuscular junction, the sarcolemma is going to become folded. This folded portion of the sarcolemma is referred to as the motor end plate. And the motor end plate is going to possess nicotinic M receptors, or cholinergic receptors, that are capable of binding acetylcholine. Now, that axon terminal is going to be housing acetylcholine within these synaptic vesicles. When a nerve impulse or action potential reaches the axon terminal, remember that opens up voltage-gated calcium channels. That allows calcium to flood into the axon terminal, and the calcium is going to trigger fusion of the synaptic vesicle with the presynaptic membrane like this. When this occurs, the acetylcholine is released from the synaptic vesicle and diffuses across this synaptic cleft. As it diffuses across the synaptic cleft, it's capable of binding to those nicotinic M receptors located along the postsynaptic membrane. Okay? Now, these nicotinic M receptors are linked to voltage-gated I'm sorry, not voltage-gated, but chemically gated channels. So these nicotinic M receptors are linked to chemically gated channels so that when a chemical, i.e. acetylcholine, binds to the receptor, those chemically gated channels open. And one of the things that occurs when those chemically gated channels open is that sodium floods into the muscle cell. And so if enough sodium enters into the muscle cell, it can generate an action potential that then gets propagated along the sarcolemma. Okay? So as sodium enters, remember it's going to be attracted to the neighboring segment of the muscle fiber, which is negatively charged. And as that sodium moves, it triggers opening of more voltage-gated, in this case, sodium channels. And so in this way, the action potential can propagate along the sarcolemma. Now, as that action potential travels along the sarcolemma and then down the T-tubule, it triggers release of calcium, which acts as the trigger for muscle contraction. The calcium is going to bind to troponin. Okay? So this linking of the electrical signal to contraction is called excitation-contraction coupling. The linking of the electrical signal to muscle contraction. We've talked about this information already. This is the neuromuscular junction. It's formed by an axon terminal, a synaptic cleft, and the motor end plate. And what it says in this slide is though the axon terminal and the motor end plate are very close, there's no physical contact. There's a space between them, and that's called the synaptic cleft. And it's across that space that acetylcholine has to diffuse in order to reach the receptors. This is kind of a space-age view of a neuromuscular junction. You can see synaptic vesicles that are fusing with the presynaptic membrane, releasing acetylcholine. Now, acetylcholine binds to a nicotinic M receptor And in doing so, it opens up chemically gated channels that allow sodium to enter and at the same time potassium to leave the cell. But it turns out that more sodium enters than potassium leaves. So as potassium floods into the cell, it causes depolarization. It causes the interior of the sarcolemma to become more positively charged. If you have enough depolarization, it will propagate an action potential. Now, within this synaptic cleft, you find acetylcholinesterase. Its role is simply to break down acetylcholine into acetic acid and choline so that acetylcholine doesn't continuously stimulate those receptors. Yes?
So when you're working out and you're like constantly contracting and whatever, is that why you're supposed to like intake more potassium? Because not like since you're having more leaves, like there's like not enough in your system.
Well, let me say this, is that relates to muscle fatigue.
I thought I was wrong, so I didn't say it loud.
And most of muscle fatigue is due to a buildup of lactic acid. Right. Now, are there some electrolyte imbalances that can develop? Yes.
Okay.
Particularly with prolonged strenuous exercise. That's why people take salt tablets and such.
Yeah.
But when you're exercising in the gym, the main reason is the buildup in lactic acid. Yeah.
Yeah, I knew that. I was just wondering if the potassium had anything to do with it, because we had to eat banana. We had to eat like banana and stuff all the time.
And that's not a bad idea.
Unless you're allergic to potassium.
Are you allergic to potassium?
Okay. This just shows again, here's the motor end plate. Here's the axon terminal. This is the neuromuscular junction. Now, everything it says here we've discussed already. It says when a nerve impulse reaches the end of the axon at the neuromuscular junction, voltage-regulated calcium channels open, calcium floods into the axon terminal. It causes the synaptic vesicles to fuse with the presynaptic membrane. This in turn triggers release of acetylcholine into the cleft. It diffuses across the synaptic cleft and it binds to receptors on the sarcolemma, on that motor end plate. Okay? And binding triggers opening of chemically gated channels that lead to depolarization. Now, it says here that acetylcholine is quickly destroyed by acetylcholinesterase. Okay? And that prevents continued muscle contraction, continued stimulation of receptors. Again, the mechanism is that you have opening of chemically gated channels. Sodium diffuses into the interior of the sarcolemma and it becomes less negative. It begins to depolarize. Now, a transient depolarization event, which can then propagate along the sarcolemma, is called an action potential. We talked about action potentials with nerves. Okay? We said that at rest, the neuron, just like a muscle cell, has a resting membrane potential. Okay? And it's due to the specific distribution of ions across the membrane. But at rest, the interior of the sarcolemma, just like the interior of a neuron, is electronegative with respect to the outside. Okay? The predominant intracellular electrolyte is potassium. The predominant extracellular is sodium. Now, with opening of chemically gated sodium channels, sodium floods into the cell, and it results in depolarization of that little patch of sarcolemma. If enough sodium floods into the cell, such that it then moves to the adjacent patch, okay, being attracted by the negative charge in the adjacent region, then it will open up enough voltage-gated sodium channels such that an action potential is propagated across the entire sarcolemma. And then, of course, down into T-tubules. Okay? So if the stimulus is strong enough, an action potential will be initiated. Okay? And again, remember that as sodium comes in, it tends to move to the adjacent patch. It opens up more voltage-gated channels, and that occurs all along the sarcolemma. And of course, on the heels of the sodium influx, you're going to have opening of voltage-gated potassium channels that allow then potassium to efflux out of the cell, leading